In the late 1990s, two teams of astronomers were studying distant supernovae to measure the slowdown in the expansion rate of the universe. That's because over time, the gravity of all this stuff slows down that expansion. But instead, they found the complete opposite result: accelerated expansion. That means that our universe is getting bigger and bigger, faster and faster every single day. We call this effect dark energy, and, well, we have no idea what's going on. But hey, at least it's got a cool name, right? That's right. Dark energy is literally the name we give to accelerated expansion. That is it. I suppose accelerated expansion has too many syllables in it or whatever. Anyway, dark energy is great branding. So what are some potential explanations for this accelerated expansion, aka dark energy? Well, one option is that it's modified gravity. Maybe we need to change our understanding of general relativity on cosmological scales. Well, every attempt we've tried to modify gravity comes up short and break observations. Okay, so that's out. Maybe it's something called a cosmological constant. It's just a fundamental constant of nature, like gravity or the speed of light, and it just exists and sits there and doesn't do anything except cause accelerated expansion. Well, that's cool, except it has no physical explanation whatsoever, and we don't really know how to interpret this. So that's out. Okay. Maybe it's something called quintessence. Maybe there's a new ingredient in the cosmos, some scalar field, don't get me started on scalar fields, that imbues the entire cosmos and fills it up and drives this accelerated expansion. But all of our models here are pretty much just made up on the spot. Okay, so that doesn't work very well. So maybe it's, I guess we're out of ideas. We're kind of stuck with dark energy. We've known its existence for over 2 decades, and we still can't understand what exactly is going on. And one of the problems is measurement. This is an incredibly subtle effect that can be only measured across vast cosmic distances and times. So we have to build massive observatories to try to get a handle on what dark energy is doing at these scales. We know that dark energy exists. We know its strength to a few % accuracy, which is really, really good, by the way, and it took a long time to figure that out. But that's it. We don't know if it's getting stronger with time, weaker in time, if it's transforming to something else, if it's interacting with dark matter or normal matter. When it comes to dark energy, we're just, well, we're in the dark, right? So dark energy is by far the most powerful player in the universe. But to show you how, I'm gonna need the chalkboard. Dark energy is the current boss of the universe. It is by far the most important component in the universe today. But it hasn't always been the case. Dark energy spent ages, billions of years lurking in the shadows before it arose from... Okay, I'm getting a little bit dramatic. Let me show you with math how this all works. We're gonna use something called the Friedmann equations, which were developed in the early 20th century as a solution to the Einstein field equations. Thank you, Albert. Really, you can share the spotlight with Alexander Friedmann? He gets enough airtime already. Anyway, the Friedmann equations tell us how the different components in the universe evolve with time and how the expansion of the universe responds to that. There are a lot of ways to write the Friedmann equation. So this is just one of them. We've got H, which is the Hubble parameter, or the expansion rate. We're gonna square that for no reason whatsoever. Divided by the present day expansion rate is related to a bunch of things. So we have, say, the current density of radiation times something called the scale factor, which is just a measure of the current size of the universe to the -4th power, plus the same deal, the present day density of matter times its own scale factor. And then if our universe is curved, it gets its own parameter plus our favorite, dark energy. Now the key component here that makes it all work is that dark energy is constant. That's one of its main properties. Dark energy doesn't change with time, and it doesn't evolve as the universe expands. It just hangs out being there. So let me show you on this plot. First off, I'm gonna ignore the curvature because, as far as we know, and as far as we've been able to measure, our universe is totally and completely flat. So we can ignore that term, at least for now. Let's see how radiation evolves. Radiation drops off as the fourth power of the expansion. So the density of radiation as time goes on since the Big Bang really drops to rock bottom here. And very, very quickly, within a couple 100,000 years, radiation doesn't really play a role in a cosmological sense. Well, there's also matter. Our universe was born with a certain amount of matter, and it just dilutes over time. The universe doubles in size, and the amount of matter drops by an eighth. It's just that simple cubic relation. And it goes something like this. Okay, that's not so bad. Now, what does dark energy do during all of this? For ages, for billions of years, dark energy is just down here, just hanging out, minding its own business, hatching its sinister plot. And then eventually, about 5 billion years ago, it overtook matter and continued just going and going and going. And today, the present day, dark energy makes up over 70% of all the matter and energy in the entire universe. And far in the future, billions of years from now, matter will be all the way down here, and dark energy will be like 99.999999999999999999999999999% of all the matter and energy in the universe. It is the dominant factor in our universe today and into the future. But to dig into what we're thinking dark matter could be, we need to talk to an expert. So we have a lot of options to explain dark energy, but none of them are satisfactory. What can we study in our universe to try to figure out what dark energy is made of or what's causing it?
Fortunately, it's hard to kind of prod and manipulate. It's very tenuous. If it has any interactions, it doesn't seem to interact with ordinary matter. It's very hard to get to in a laboratory, Earth laboratory perspective. But we can see how the universe expands and measure that extremely precisely. Look at all the dynamics on larger scales where this dark energy density is actually the dominant contribution, because the universe is mostly empty, is a very, very, very empty place overall. So if you look in underdense regions, for example, there dark energy would produce, almost the entire energy density there. And so we can study those, see how they expand, exactly how it started accelerating, use every single way that we can determine the expansion geometry of the universe in the most precise way possible.
If you had to make bets, what do you think the best explanation for dark energy is?
I'm not a betting man. There's really not very good theoretical guidance at the moment. I prefer taking one particular explanation, which in some ways is the simplest, which is just adding this extra constant, and just turning all of our firepower on this explanation and do what scientists do, which is to test and test and test that model and see if it fails. For example, with upcoming data sets like the Euclid space mission, Vera Rubin Observatory, LSST survey, DESI, large survey of the universe, all of those will provide us with a tremendous amount of data that will allow us to do these geometrical measurements. And there's really a wonderful set of complementary measurements you can do. You can look at how bright things are as a function of distance. You can look at how big things appear as a function of distance. If you can find objects or collections of objects that collectively ought to be spherical in ordinary space, you can see how quickly they expand along the line of sight, because the universe is expanding, compared to the size of them. And that gives you a way of measuring the expansion, not just where we are now, but actually at the distance of these objects. What's also very, very interesting about this is that we can now take all of the wonderful progress in machine learning and in deep learning and actually analyze every single galaxy that we see in the universe. The dream is just to take all of that information and model it and then extract the most precise measurements we can. And already, actually, we're at how close the observations say that we have to be to something like a cosmological constant. It's beginning to hurt already. So if we can just improve the constraints by a factor of 10 or 100, a huge rethink has to happen in terms of how to embed what we know about cosmology with those theorists thinking about theories of quantum gravity, like string theory.
There's very little theoretical guidance when it comes to trying to understand dark energy. Why is dark energy so weird and so out of bounds of what we understand to be physics?
We actually have phenomenological models, so we can make the universe accelerate because we have general relativity, and that has that option, right? You can turn pressure into tension, and that causes gravitational repulsion. Whenever you take typical particle physics models that have this property of vacuum energy, that vacuum energy just always rides up to the largest admissible scale in the model. So you run into this cosmological constant problem where the predictions just get way too large. And so then you need something that protects that, and it's not really clear what that would be.
What's the biggest unknowns when it comes to dark energy?
We wish we knew how it relates to fundamental physics. We know that what we currently use to describe most of the universe works extremely well. The theoretical framework that we use involving general relativity, quantum mechanics, at some point have to stop working. And so we know that there is something beyond, because in certain regimes they're not compatible with each other.
How long is it going to take to figure out dark energy? When will it happen?
From an observational perspective, we're hoping to really get much better constraints on how the universe expands, really probing dark energy over the next decade. For about 30 years, 40 years, there's been an exponential growth, not just in the size of the universe, but actually in the amount of data that we have about the universe. And we're still in that exponential growth phase. Every moment is qualitatively different. And so we're still in this exponential growth phase with data and cosmology, with these surveys that I mentioned. Qualitatively, what we know about the universe is about to be changed in the next decade or so. Other aspect which is interesting, so in a universe with an infinite future of accelerated expansion with driven by dark energy, you have an infinite amount of volume and an infinite amount of time. Since we know that in a universe where quantum mechanics also exists, quantum mechanical fluctuations can produce weird things. You can have a wall, and a particle that's on one side of the wall can suddenly appear on the other side of the wall. It's a fluctuation. Now, if you have an infinite amount of time and an infinite amount of space, weird things can happen and will happen. Suddenly, you can have the appearance of a whole fully formed planet just fluctuating out of nowhere. In principle, you can actually have a new beginning. So in some sense, this infinite future of accelerated expansion where the universe is just empty and cold and stars extinguish, black holes decay. It seems like a death scenario for the universe. But in principle, at some point, just through random fluctuations, you can fluctuate new things into existence. This is sometimes called the Boltzmann brains scenario. Basically, you can have a fluctuation appear where there's an Earth with everybody on it, and everybody remembers their history just like we remember our history. And in fact, we don't really know whether we might have been fluctuated into existence just like that. Of course, it's unlikely for a whole functioning universe to fluctuate into existence as we observe it. So that's probably not what happened to us. But you can have these kinds of bizarre situations happening when you have an infinite future ahead of you.
Well, I'm glad to hear that the future can be very weird. Thank you so much, Ben. So dark energy is by far the most dominant factor in the universe. But how does dark energy actually create accelerated expansion? Well, check this out. It's a real mind trip. We live in an expanding universe. And this universe is full of galaxies. And that means in an expanding universe, slowly over time, on average, every galaxy gets further away from every other galaxy. This is creating space. Over time, there is more volume, more empty space in the universe. Okay, hold on, we're not there yet. So let's assume that dark energy is somehow tied to the vacuum of space. It's a property of the vacuum of space itself. So this would work if dark energy is a cosmological constant or in one of the quintessence models. We'll leave modified gravity for another episode. So as time goes on, our universe expands, there's more empty space, and there is more dark energy. We are creating dark energy by the second. And if you're wondering, how can that not violate conservation of energy? Well, it just doesn't, okay? It's fine. You're just gonna have to live with it. Anyway, so there's more dark energy as the universe gets older. Okay, we're not quite there yet. Hold on. To finish this story, we need to bring in our good friend, Albert. Thank you. We know from general relativity that different sources of matter and energy can have different strengths of gravity. Some can be weaker, some can be stronger. And you know what? In general relativity, anti-gravity is allowed. Gravity can be repulsive. You just need something special, something very special and unique, like a rubber band. That's right. This rubber band has mass, and so it has a gravitational attraction, the normal kind of gravity. But when I pull on the rubber band, it also has tension. And in the mathematics of general relativity, the tension in the rubber band itself creates a repulsive effect, an anti-gravity effect. Yeah, it's true. I mean, you don't normally feel this with a rubber band because the attractive portion of the mass, that normal gravity, is so much stronger than the repulsive effect of the tension itself that you don't really measure it. But hey, that's a rubber band. When it comes to the whole entire universe, it's a completely different story. You see, dark energy has a very, very crucial property. It has tension, and that tension creates a repulsive effect. So as our universe expands, there's more and more dark energy, so there's more and more tension, so there's a stronger and stronger repulsive effect, which drives a faster expansion rate, which gives us more volume, which gives us more dark energy, which gives us more tension, which gives us more anti-gravity. It's a vicious feedback cycle that drives an accelerated expansion of the universe. Ow. You may have noticed that I've spent most of this episode not really explaining what dark energy is. There's a reason for that. We don't know. We don't know what dark energy is. We're really in the dark. We simply don't have the precision to tell us which model is correct and which model is wrong. But in the past few years, there has been something very interesting to appear on the cosmological scene. Astronomers are very interested in measuring a particular number called the Hubble constant or Hubble parameter. This is the present-day expansion rate of the universe, and different measurements are giving different results. And one set of measurements from the early universe are telling us one number, 68 kilometers per second per megaparsec. But other sets of measurements from the later universe are giving us a different number, a higher number, somewhere around 72 kilometers per second per megaparsec. Now, these numbers are not very different, which is awesome and a testament to how great we're doing at cosmology, but they are statistically significantly different, and we can't explain this difference. It could be that dark energy is evolving and dynamic and causing this shift in the expansion rate, or it could be something else entirely. We honestly don't know. We don't know what dark energy is, and we don't know what dark energy will do in the future. Dark energy could be completely constant, and it will just maintain this accelerated expansion for eternity. It also could be that dark energy gets stronger with time in a scenario we call the Big Rip, in which case all things in the universe, including galaxies, solar system, planets, and even you, will get ripped apart at an atomic level in less than 1 billion years. Or it could be that dark energy eventually just fades away.